You're on recording.
All right, cool. So, a lot of the work I think so far that's been discussed as far as working group coming from Marcel's and Tom's end has been about getting logs out there, getting more instrumentation out there so that we can do stuff with it. Right. So Marcel has that operate first cluster data and logs that he or someone else is going to talk about soon. Tom is working with some of my students and deploying some microservices in the operate first cluster so we can get logs and data from that. A different angle is also, what can we do? What are the more advanced tools we can build using all of this data or versions of this data? The interesting interplay there is simply, if you want to build more advanced tools, are there requirements they impose on the data that's being collected so we can actually create these sort of tools? So I'm going to spend some time talking about some research that my group's been doing for the past little while now. What you folks are going to tell me is, why it won't work. You're going to tell me if you wanted to get this as a tool out to real people, what we'd have to do, and we can go from there. Right. So I'm going to share. We're going to do this interactively. So I'm going to share my whiteboard. Except apparently I can't share my whiteboard. Let's see. Jen, could you enable?
Yep, getting that done right now. Hold on one second here. Share screen. You should be all set, Roger. Let me know if you're not.
Cool. I get my screen to rotate and then share, AirPlay. So. All right. No.
This is a very whiteboard.
Yes, cool. So we're going to do this interactively, right? So this work that we've been working on is called, the acronym is unfortunate, maybe it's not the best acronym. Right now it's called EAIF, which is known as variance-based instrumentation framework. And the problem that we're trying to address is a very standard one, and it's that we like to add log statements in lots of places to help us debug our code, except how do you know where to add a log statement in order to debug any specific problem in the system? And so all of us have been through this very time-intensive process of like always going through trying to debug a new problem. We focus specifically on performance, but say debug a specific performance problem, and find that whatever logs or instrumentation we need to debug it just isn't present in the system, right? So what we do, we go add more log statements, or we like enable a higher debugging level. We go look for the problem again, see if whatever we have is sufficient to help, and keep doing that, right? And we argue that this is a time-intensive process, and we can reduce it so that folks who are debugging problems can kind of get the intuition they need right away to figure out the root cause. We'd all be in a much better place. So, problem, But if you have any questions or comments, feel free to just blurt them out. And so what we claim in this work right now is that the combination of combination of distributed tracing plus some key statistical insights about performance variation. And I'll go into a bit of detail about this in a bit. And so what we've come up with is basically a tool, which is a push button approach to enabling more log statements, essentially tracing instrumentation in your system. So what happens is that you start out with some basic level of traces, or you can think of them as logs, same thing, right? Tracing and logs are very much the same thing. Basic level logs, or trace points, so I'll call them for now. So you're running the system as you normally do, you get your traces, you get your logs, and you find that there's some new performance problem, some request is slower than it used to be. And you want some additional instrumentation to be turned on to help figure out where that problem is coming from, right? So what you can do with this tool is you can push a button. And this tool will automatically turn on the logs / trace points that it thinks are needed to kind of provide more insight into the problem. And I should note here that this tool is agnostic to how the instrumentation is enabled. So it could be dynamic instrumentation. It could be something that's injected into the system, right, dynamically, or it could be just like static instrumentation that is reading control signals and deciding based on the control signals whether or not it should emit a record of the log point execution and store that somewhere. Yeah. So. It could be. Okay, cool. So that's the high level of the tool. Let me go a bit more detail into why we're doing this, and then I'll talk a bit about kind of the design for this, and then what we've done so far. So let me find.
One quick question. Do you hear me?
Yes.
Okay. Is the kind of logs and tracing points known before you push the button, or are you dynamically adding those tracing points?
So the argument here is that this type of tool lets you do have to know the possible points where the logs could be turned on, right? So the tool needs to know this. It's going to pick from this large set of possible choices. What we'd argue in this work is that this sort of tool gives you the freedom to add as many choices as you want to your system, because they're not all going to be turned on, right? And now you have the flexibility of the tool saying, okay, I really want just these 10 out of the 1,000 or whatever else that it could turn on, right?
So expressed really simple, it would be in cranking up the debug level while the system is running for a certain subset of
Yeah.
nodes or parts of the whole
Right.
system. Okay.
Exactly. So let's talk a bit about motivation. I like using different colors, so I'm going to use orange. So if you look at just looking at the literature on debugging, there's lots of work that complains about a couple of different things. The first one is this lack of, one size fits all instrumentation, right? So basically, we can add tons and tons of log statements to our application, but we have no idea if any specific one is going to be useful for debugging a specific new problem that we're going to see in the future. And so if you look at a lot of a lot of message boards, or you look at a lot of developer forums on some open source applications, you'll actually see these fascinating fights where people are like, you know what, I really want this thing to be turned on. I really want this log statement here in this code because I think it's useful. And this other person like, no, that's going to add too much overhead, right? We can't do that. And so there was a paper that actually showed that in one specific system, almost 30 or 40% of the revisions to this code base was simply either adding more information to the log statement, removing it, turning on the log statement, or turning off the log statement. So basically the people are having these fascinating fights about what instrumentation you want to have in your system and what should be collected, right? And so this leads to this tussle, if you will, between informativeness and overhead, right? So how do you break this tussle? So
Raj, I have a quick question for you. Is this turning on and off the generation of messages, or is it more like a filter, so it is controlling what messages you see?
Right. So we're trying to take the extreme case of turning on and turning off messages. Because guess what? Okay. We're in academia, and it's my job to try and do stuff that's more extreme, right? Everything I say could be applied to the case where you're filtering messages, right?
Right.
I do think that the decisions the tool makes could be more optimal if you take the approach of filtering, because you already have everything turned on in the first place. At the same time, the trade-off is that you do have to have everything turned on in the first place, and you have to cache everything somewhere for some amount of time, and you're paying some of the overhead of actually having them on. So I think there is a fundamental trade-off there.
Okay.
So I would argue. Oh, sorry, go ahead.
I was just going to say one counterpoint that I run into far more often than you would think is that the act of actually engaging log generation in an application significantly alters its performance profile, often to the extent that subtle race conditions that you were hitting in the application when that debug logging wasn't engaged are suddenly being lost when the debug logging is engaged. And so you get a Heisenberg effect where you're not able to log the defect because it wasn't occurring with the debug logging on. So I mean, that seems like at least under certain circumstances, argument in favor of always generating the debug logging so that you have a known consistent performance profile, but then filtering the logging as it's coming out of the application suite.
Right. I mean, I could view that in two ways, right? So that's very interesting. So you can say that, hey, look, I'm just going to have the debug logging turned on all the time, and I'm always going to try and pay the overhead of that. And this way, the system is more consistent, right? But, you know, like you're paying the overhead of all that instrumentation, and you're probably still now have to make that choice of, you know, what should be in the debug logs. The other argument is, could you turn on the instrumentation in a fine-grained way such that you're reducing the potential for these Heisenberg effects? So I think that I still think there's like an interesting trade-off there, if you will. Would you agree with that, or would you want to offer another counterpoint?
No, I think that's a good answer.
Yeah, and I would even fully support the idea of being able to continuously profile or continuously log a subset of your fleet. And there has been a bunch of blog posts, I think from Google, where they were saying, if you have turned on instrumentation for a 0.1% or even a smaller portion of your systems, that's super valuable data, and you're just reducing the performance of a very small subset of your requests anyway. But going even more, and like what you're suggesting, turning that on demand, I think that's going into the right direction, because we don't have systems that are made out of 1 or 2 servers anymore. It's like 100 servers and today, and 1,000 servers tomorrow, and 5 on a holiday, right? So it's super. We have to think in percentages, anyways.
Okay. So challenge 1 is this lack of one-size-fits-all instrumentation, leading to this tussle between informativeness and overhead. And so arguably, the requirement this is introducing, I should do requirement in red. So the requirement this introduces is that you want to be able to turn on instrumentation dynamically, right? Turn on instrumentation selectively during runtime. And arguably, this is the reason why we have dynamic instrumentation approaches, right? There's like dtrace, right? There's pivot tracing, the tracing world. There's Fay, which uses like hot patching to let developers add log statements or anything they want on function entries and exits, right? So this already exists today, right? The second challenge that we have is that, great, you have dynamic instrumentation, but you still have like this extremely large space of possible points you can insert your logs. Right, so like, it's just like every function entry exit, maybe something more granular than that, right? There's still going to be like thousands or hundreds of possible logging locations depending on your system, right? So you're either really relying on developer expertise to figure out where to start, right? Or you're gonna be spending a lot of time playing around where you want to add these log statements. And so this is where we want to introduce this requirement of automation, right? So the instrumentation framework itself, or the logging framework, should be automated in some regard. Right. It should be automatically capable of narrowing down the search space. Possible choices. Great. And the third thing is, like, you might do all this stuff, right? But sorry, I keep forgetting to change my colors. You might do all this stuff, but there may be multiple problems in the system, right? We can't be naive. We can't assume that we're focusing on performance problems specifically, right? We can't assume that logs are used just for diagnosing problems, either corrects performance. Like what we've been reading is like people use them for all sorts of things. They use them for accounting, they use them for auditing, and so on. And there might be multiple, problems in the system at the same time, right? So the other challenge you see in the literature is that they'll say that we have a problem of data overload, right? Right. So there's just so much instrumentation turned on, and you're trying to debug a new problem, right? Like how do you navigate that set of information to find the specific thing that may exist in those logs or may not exist, right? I think addressing the previous challenges gets us to reduce this needle in the haystack, but still, there may be competing problems in the system. There may be logs enabled for different purposes. And so as a result of that, we also want to introduce this third requirement, right? The third requirement is, which is these automated frameworks. Their logging decisions. So this is going to turn on some instrumentation. It should tell you why it did so, right? And this would both avoid this needle in a haystack problem because, hey, look, it's telling you exactly why it did what it's doing. As a result, it's also going to be super useful for diagnosis because, hey, look, the tool is trying to reason about things in maybe some very basic way, but still, you kind of know why it's doing what it's doing. You kind of understand its quote unquote thought process, if you will. All right, so I don't know, Tom, what do you think? Will like spending another 10 minutes make sense? Or, sorry, Marcel, or do you want to switch to the other talk sooner?
I don't know, Anand, what's your expected time of your talk?
Like 15 minutes, 15. Yeah.
Okay, I'll wrap up in like 10 minutes then. So I'm going to quickly go over why we think we can add this with a combination of tracing and some insights about performance variance. Right? So insights. And here I'm going to use this very cool functionality that Apple has that lets me copy something from my laptop and paste it here. Let's hope this works. It's working on it. Hopefully I didn't give them credit before. For this view. Let me try that again. Ah, there we go. So let's just move this down here. So quick overview of how tracing works for those of you who aren't familiar with it. What you see on the bottom is a distributed application. We're just throwing OpenStack as an example. The little rounded rectangles are logging points. We call them trace points in tracing. The only difference is that whenever the trace point is executed, it also logs a trace ID or request ID plus some logical clock information that lets us differentiate which log statements or trace points are executed and tackle which requests. And that request ID or trace ID is propagated alongside with the request itself. So here's our context thing. So logging and tracing are basically the same thing. You propagate request ID with your request. You have to propagate that across RPCs. You have to propagate that across process boundaries, across thread boundaries. That may be hard, but that's what it takes to get tracing. When a trace point is executed, right, you record both the trace point information, which is the name, plus any other information you want to record at that point, right, such as like function parameters or or input parameters or client parameters or whatever else. And you also add the context, a request ID, and maybe some logical clock values if you want to order the trace points. So all those trace points are basically cached at local agents, right? Usually it's a fixed size in-memory buffer, and that buffer will be discarded. Trace points will be discarded if that buffer fills up. And then at some point, there's a trace collector that grabs all those cached trace point records and then stitches them together based on request ID and the logical clocks. And what you get are these traces, right? So it looks like all these arbitrary terms, A start, B start, and these are just trace points, B end. And the most general way you can think of tracing as where nodes are trace point names. And edges happens before relationships. Plus latencies. And also each trace records response time of the request. All right. So I will very quickly go over what the insights are. So the first insight is that, there's a reason why we have things like performance counters, right? There's this very basic expectation in our distributed applications that requests that kind of execute that have the same workflow through an application or a distributed application, and execute the same functions, right? Do the same work, right? Should perform relatively similarly, right? And so, we have counters for writes, we have counters for reads usually, right, in a storage system, right? There's just this basic expectation that things that do very different work should perform differently, and things that do similar work that kind of are processed similarly by the application should perform similarly, right? So insight one is there is this expectation that requests with similar workflows, right? Specifically with similar critical paths, right? Because the critical path is what determines performance. And what this means is that if they don't, there's something interesting we don't know about the requests. These requests. I'm going to really add one word here that may be useful, and that is I'm going to add the word with similar critical path traces and something we don't know about their traces, about their request traces. Right. So this is basically a way of pinpointing, hey, look, if two critical paths from their traces look very similar, right, and yet they're performing very, very differently, there's something that's really interesting that's going on that we don't know, right? What could that be? Right? It could be like a slow, uninstrumented function. This just isn't showing up in the traces. So the critical paths look identical, and yet one request is executing this function and the other one isn't, right? It could be like interesting, like, you know, like heterogeneity, right? So it could be like caching behavior. Maybe there isn't instrumentation around an important cache. And so we're merging together requests that actually perform very differently because some requests are being stored at a cache and some aren't, right? It could be load imbalances, right? Maybe a request is being load balanced across many different machines, and some machines perform differently than others, and we don't have the machine name, so we can't differentiate them. So the first insight is that there's this thing about similar critical paths, similar performance. The second insight is that tracing lets us get these traces of critical paths, but resolution equal to the amount of tracing instrumentation that's enabled, the amount of trace points are enabled, right? So insight 2. Yeah. Tracing. Obtain, you know, graphs of critical paths as per the and the third insight, which is kind of cool, is that you can actually take, so let's say we take all the critical path traces that look identical, like they have the same trace point names, they're executed in the same order, right? And we group them together. We find their variance and their response time is really high. So there's some behavior that's interesting that's going on that we don't know about, right? It's a critical path, right? And it turns out that, you know, variance decomposition has a very simple property, and that is the variance of the sum of a bunch variables is equal to the sum of the variances. Yeah. Plus their covariances, basically. So what this means is that I could have a bunch of traces that look identical, a bunch of critical paths that look identical, right? And I find that their response time variance is really high, which means that there's some interesting behavior that's going on that might be a problem, right? If I know their latency distributions of the edges, which are basically latencies of the code areas between two successful trace points they execute, right? I can actually say that I can actually figure out the largest contributors to the overall variance or all response time variance by figuring out the largest contributors, the largest variance across the individual edges, right? So if I look at this and I find that this guy variance is really high and that one's really low, I know I can focus on this one. Right? And so that gives me insight about between any two trace points, what is the variance? What is the interesting unknown? Where is the interesting unknown behavior coming from? So one simple example of this might be, what do I have here? Yeah, let me copy and paste this. So one example here might be, here's a cache hit versus cache miss example. Hopefully we'll paste. Give it another 30 seconds or 10 seconds. No, that's the wrong picture. Come on, you can do it. All right, so it has decided it no longer wants to work. I gave Apple credit where I should not have. But basically, I was going to say that you might find that most of the variance comes from here. And it might be a caching behavior. It might be there was some instrumented caching function that you didn't know about. It could also be contention, right? So it could be that as part of your trace point, if you had exposed something like queue lengths around the resource, right, you could find that that the queue lengths correlate really well with the observed response times, and you can add bins of the queue lengths to your trace point names, and now you could differentiate your groups of identical critical path traces based on the amount of contention they experience. Finally, like your request could just be consistently slow, right? It could be that like they exhibit really low response time variance. It's just that all of those are in the tail of some distribution, right? So once you've sorted out the variance sources, you can then kind of figure out, oh, look, what are the remaining functions that are just always slow? And you could kind of zoom in on those in a very similar way to what we discussed, and you can enable instrumentation there as well. So those are kind of the three driving insights behind this tool we've created. I'd love to draw a picture of this tool, but I don't think I can copy and paste anymore for some reason. Let me try it one more time. Let's see if we'll do it. But basically, we built a tool. What it does is that we've modified some existing tracing infrastructures for some systems to allow their trace points to be kind of selectively enabled or disabled. We put in some control logic, almost like a control plane for tracing, that uses the insights I just described to kind of decide where to enable more instrumentation. So what does control logic take as input? It takes as input, one, what are the trace points it could enable or disable? It takes these quote-unquote search strategies, which are ways to navigate the trace points that could be enabled or disabled between any area of the system. And it takes as input two thresholds. One is what it should consider as high variance, and B, what it should consider as consistently slow. So the former, whatever, the latter for consistently slow, you would basically say something like, for different API endpoints, right, consider anything above the 95th percentile of response times as consistently slow. For the former, for the variance thing, we actually specify that as a coefficient of variation. So we specify that as a normalized dispersion. So it's standard deviation of the mean. And that kind of reflects the insight that requests that are more unpredictable, if you will, that is that their response times vary a lot compared to the means, might be more interesting than ones whose response times don't. And what this tool will do is if you push the button, it will go identify the majority of the variance sources for requests that exhibit high coefficient of variance, and then the majority of the latency sources for requests that are consistently slow. And in the process of doing this, it's basically a continuous cycle. Let me try something like that. Nope. Where it is basically figuring out where variance comes from, enabling more instrumentation there as per the search strategy, regrouping all the requests with identical critical paths now, right? Figure out which ones still have high variance, doing the same thing over and over again. So kind of zooming in more and more on the variance sources. And then also doing the same thing on the consistently slow latency sources. So that eventually you have traces that where the instrumentation enabled explains all the variance and basically explains all the sources of latency in your system. All of this is modulated by the available resources. So we're also monitoring the queue lengths of the tracing agents on each node. They're actually caching trace points. And those things are in danger of overflowing. This tool will pause and stop so that we don't end up basically generating false positives, saying we enabled instrumentation, but hey, look, that instrumentation was dropped. It didn't show up in the traces anyway. So we don't want to claim we did something when we actually didn't. So the tool stops when the queue lengths of the tracing agents are getting full. And also, like, the last innovative thing that I didn't get to talk about was that it maintains the history of its decisions in essentially a tree. So basically, as it's enabling more instrumentation to explain variance or latencies, it turns on the instrumentation, it measures variance and latencies before and after, and it gives you that in a tree. So it says, okay, I turned on this instrumentation, requests that now executed that tracing point, right? Their variance and latency characteristics look like this. Requests that executed and didn't execute that trace point, their latency and variance characteristics look like this. So you can actually walk backwards in this tree to figure out why instrumentation is enabled on behalf of the problem that you're seeing. And that's about it. So like, we have a tool that does this. It currently works on OpenStack and it works on HDFS. I'd love to get folks' input on like whether you think this would be useful, what are the showstoppers, how else should we be enhancing this so that we can make this a usable tool by other people. And with that, I should stop.
Yeah. That's super, super interesting. And I already asked Anand if he would be okay if we defer his stuff to the next meeting, because I think if we would just do a hard cut here, we are missing the chance of actually discussing what you just presented, because I think it goes into a lot of directions where it could be applied to, and I don't want to dump my brain just yet, and give others the chance to chime in. Otherwise, I have some notes.
Let me share a different screen of the diagrams so that folks can actually see that. Since my copy pasting stopped working. So hopefully you can see the screen here. You can see this is the basic design diagram. So basically we now have an instrumentation plane, which is an application that's instrumented with tracing, right? And it has trace points that can be selectively enabled or disabled. And then we have control logic on top of it, which is using the intuition that I described to try and figure out where to enable trace points. And the red thing kind of shows the continuous cycle. So we turn on instrumentation to control logic, we measure the new traces that we get, and then we turn on more instrumentation. And we stop at some point. All right. Questions, comments? Tell me why this is a horrible idea.
Somebody? So I think it's a great idea. I don't think it's a horrible idea. I think turning on these knobs on the fly, that's like the holy grail, right? So in some articles on observability, and you used logs and traces interchangeably, and I think that's in essence what it boils down to. Even using metrics and traces. In the end, if you have everything instrumented, you can recreate logs and metrics out of your traces anyway. So I think it all boils down to turning on those knobs for traces on demand so that you can generate your logs and your metrics on demand as you need them. That's the crucial path. And there's so many applications for this kind of logics, and I don't want to go down into every bit just yet. Just for my understanding, OpenStack is the compute platform that you're deploying that to, and is HDF as the application that you're instrumenting?
Yeah, HDFS is the application instrumenting, and OpenStack is the compute platform. Yeah. We chose those because they had some basic form of tracing already present. We did have to modify that, but like one of the challenges we have in this sort of research is that it's hard to find open source systems that have a lot of good tracing instrumentation already. Like Facebook and Google are doing their own thing, right? And they have tons of systems with tracing enabled. In the open source, freely available software world, it's a bit harder. When people add tracing, they often take the most, perhaps because of the challenges we described, they take like the most minimal, basic definition of tracing possible, and they use it, which makes me very unhappy. OpenStack and HDFS had a decent amount of tracing in it already, so that's why we chose those. Torsten, I want to point out one thing, and that's that people often talk about like these three pillars of observability, which is like logs, metrics, and traces. And this has always bugged me because you hit the nail on the head there, right? Like you should be able to generate the other two from your traces. So fundamentally, they're the same thing. Yeah. Maybe as a result of overhead, they're different things, but like there's no fundamental reason they should be different.
I guess it was a matter of evolution, right? So we started out with just spreading some printf statements into our code, and then somebody said, oh, we need to aggregate those printf statements, and somebody came up with metrics, and then somebody said, okay, no, it's just a distributed systems, and how would I link those together? And somebody came up with, oh, let's slap an ID in front of the log line, and tracing was born. And if you now take a step back, it's about observing your system, and then it all kind of falls apart. There's not these three pillars anymore, but it's just giving you the capabilities of observing your system. And just like we just had the Heisenberg, right? So if you're observing something, you're fundamentally changing the system. So you don't want to have that observation on all the time, probably, but just for a subset, and then super sample and extract the real deal out of your statistics. So and then by having that capability of turning these things on and off on demand, you don't want to do that as a human per se, but maybe have an AI doing that on demand, which opens up again a whole box of applications of and research. How do I create an agent? Can I do something with reinforcement learning of an agent that is just turning on those traces on demand and just see what happens? Or this chaos engineering, chaos monkey of doing things all the time in your production system and creating insights out of it. Then how do you visualize these insights, right? So now you store all your traces and all your stuff, but how do I actually work with this? So I think it spans the whole topic, the whole domain of observability.
Right. So there's a couple of things you pointed out there that I want to touch on. One is I do view this as a platform or a framework on which to do a bunch of other interesting things. Like you mentioned reinforcement learning, right? Like these search strategies that are in here, right? There's like this huge opportunity to explore much more advanced search strategies than the one we have, perhaps based on things like reinforcement learning in the future, for example. So I view this as kind of like a framework where we have like the basic kind of framework down. We have potentially simple solutions in each piece. In the future, I'm hoping you can explore much more advanced solutions to each of these pieces. The other thing I want to point out is that I think what this sort of research points to is that, at least from the research end, I want to be able to pitch tracing, and I've wanted to do this for a long time, as a fundamental substrate on which to build other things. In order to do that, like, I think that it would be very cool if the open tracing world moved towards generally having a control plane and APIs for a control plane for tracing, right? So right now we don't really think of a formal control plane for tracing. You kind of have, you set a sampling strategy, you kind of have a static set of trace points you have enabled, and that's kind of it. I think the backend collector lets you adjust sampling rates for different services based on like some input file. But this is really ad hoc. Like if we could formalize what are the control plane inputs for tracing, then you could layer on all these more advanced stuff that Marcel was talking about, right? In kind of an independent way onto any tracing infrastructure. So I think that's an interesting insight from work like this is, you know, the next generation of tracing doesn't involve a control plane.
I asked in the chat whether you'd seen any of John Zinke's work, because what you're talking about, particularly with the control plane for doing tracing, has been that's been a long-term thing that's been studied in networking because of searching for networking issues in a distributed system, and you know, places where you can turn on and off statistics selection in the network itself. And if you haven't seen what he's done, I would be interested in inviting him to come to this group, because I think a lot of what he's done is relevant, even though you're looking at a different type of tracing because you're going down further into the operating system. A lot of the frameworks would be useful, I think, to know about for this too.
I have not seen any of this work. I will definitely look it up, and we should definitely invite him.
He's from Akamai, but he used to do a lot of work previously to that on distributed systems in military networks.
Very cool. Does this mean
but he's still doing research at Akamai, so I can invite him if you're interested.
Oh, very cool. He went to BU. Okay. Looking at his LinkedIn profile. Yeah, that'd be great. I'm obviously, you know, like, you know, control planes in networking are like that's like a very like well thought out, very well principled way of dividing like the thought process from like the actual execution of like routes and so on. Yeah, I'd love to see what he's done in this regard too. I'll look it up.
Cool.
The other thing I want to bring up is everything we've done so far is at the application level, right? I completely believe that I have this hypothesis that application level instrumentation is worthless, and that like all of the interesting variation and all the interesting issues are actually stemming from like the virtualization platform, the kernel, right? The specific machines you're running stuff on, and so on. We get hints into lower layers where you consider like any parameters are specified in trace points as part of what we're doing. But I think that more formally being able to say very quickly, hey, look, all of the variance, all the interesting heterogeneity is not coming from your application. It's coming from some underlying layer, right? Why are you even looking at instrumentation in your application, right? Being able to say that in a principled way would be very useful. And like, I would love for this thing to be like this end-to-end framework that is actually controlling instrumentation in multiple layers, maybe the application and the kernel and the virtualization platform. And then saying, oh, look, guess what? The application, nothing's useful there. Let me just go focus on the next layer, or let me go focus on the next layer. And so the question there is, what is the bit of correlation you need for instrumentation across these layers to allow us to do this sort of cohesive analysis in the future?
Like we only have 1 minute left. Can I ask one simple question, and probably it's just your gut feeling, since this is on OpenStack and HDFS, porting this to a cloud native instrumentation framework and on containers, would that be a super challenging task, or do you think all the bits and pieces are there already?
I think that the bits and pieces are there already. There is actually a master's student who's working on porting this to some microservices as is. I think the bits and pieces are there. I think that what we need to do is kind of be more formal about separating that control plane from the instrumentation plane. And we hope to actually release the control plane portion as like an open source tool that could then be hooked into other tracing frameworks in the future. And so hopefully we'll do that at some point. I will say this is a very interesting thing about tracing that causes a problem. And that's that unless you're at Facebook, right, or at Google, the existing open source tracing infrastructures don't actually capture synchronization, and they have no easy way to do it, right? So when you get critical paths from your tracing infrastructure, like your open tracing or open telemetry tracing infrastructure, you're not necessarily getting a true critical path. You're getting a longest path. Okay. So like there are some fundamental instrumentation limitations of the underlying tracing infrastructure that might impact the utility of this tool. And I'd love to be able to sort those out in the future. Facebook actually directly captures synchronization by exposing APIs for it. And Google learns it over a large number of traces, by looking at which things kind of execute concurrently and which things kind of execute one after the other. And then they reorder their trace points based on it. And if you look at a lot of the other academic papers on tracing, you'll find that they assume that you can get true critical paths. And they'll just say that. And the fact of the matter is that you don't currently, the open telemetry. So I think that's one interesting thing that it might be interesting to chat with folks about in the future.
Awesome. So Heidi, if you reach out to this John Zinke,
yes, I will.
that
Yep.
would be super awesome. Raja, is your paper, is that on archive? Archive?
It's in submission right now, so it's not archived. We are going to clean it up and hopefully put it on archive.
Okay. Because I'd like to forward this to our tracing, to the Red Hat tracing team, which has been on this call previously. Probably everybody's on PTO there, and get their input there.
That'd be great.
And then
I'll send you an email of the paper.
Awesome. And
yeah, I'd like to see it too.
Sorry, Anand, for deferring you again to the next meeting. That doesn't mean that your content isn't valuable, but I think our lesson learned is one topic per meeting is definitely enough. So,
Yeah, I can just add more stuff to my presentation for the next time.
awesome. Cool. Maybe some logs from this insight thing here. I don't know. Thank you. Let's see you in a month.
Yeah, and
maybe.
thanks for listening and giving your
Thanks. I
thoughts.
think that was great.
Yeah, thanks. That was interesting.
Bye.
Bye-bye.